Consider these two sentences. The dog bit the man, and the man bit the dog.
Right.
If you are a software engineer building an application on top of a language model, these two inputs require completely different real-world API calls.
Absolutely. Completely different.
Yeah, for the dog bit the man, your system might trigger, I don't know, a webhook to animal control.
Sure.
But for the man bit the dog, you are probably routing that payload straight to a psychiatric evaluation service.
Yeah, that's an escalation.
Right. And the meaning is entirely 100% dependent on the sequence of those tokens.
It is. And that highlights one of the most elegant, really fundamental engineering paradoxes in modern artificial intelligence. You build this incredibly powerful multi-billion parameter engine, and then you realize it is fundamentally missing a core component of human reality.
The flow of time.
Exactly. The flow of time sequence.
Well, welcome to the Deep Dive. I'm your host, and joined as always by our resident systems expert.
Great to be here.
We have a massive stack of source material from the LLM Mastery series tonight.
We really do. It's a great stack.
And we are looking at how system designers essentially hack the concept of sequence into architectures that are inherently blind to it.
Blind is the right word.
Because at its core, the engine driving modern AI, the self-attention mechanism inside the transformer, it suffers from what we call the bag of words problem.
It does. It really does. Because when a transformer processes text, it treats the input like a set, not a sequence.
Okay, so for anyone who might be slightly rusty on the internal mechanics, let's break that down.
Sure. So every single token generates 3 vectors: a query, a key, and a value.
Right.
Think of the query as what a word is looking for. It's search parameters.
Like what it wants to find in the sentence.
Exactly. And the key is what a word has to offer to others, like metadata tags.
And the value is the actual payload or meaning.
Right. So the system computes dot products to compare every query against every key to see which words should pay attention to each other.
So it's essentially a massive, highly parallelized networking handshake.
That is a great way to put it. But the catch is that a token sitting at position 1, comparing itself to position 5, uses the exact same mathematical dot product as if you swap them to positions 5 and 1.
Oh, wow.
Yeah. At no point in that massive matrix multiplication does the attention mechanism natively care where a word sits.
So it just takes the words the dog bit man and the throws them into a bag, shakes it up, and tries to extract meaning.
Just shakes it up, yes.
Which, I mean, from a systems architecture standpoint, that is brilliant for parallel computing.
Oh, it's incredible for compute.
Because order doesn't dictate the computation sequence. You can calculate all those attention scores simultaneously across thousands of GPU cores.
Exactly. But language, code, music...
They are sequential.
They are. So if we have this positionless system, we have to inject position back into it before the tokens even enter the attention mechanism.
Before they even get into the bag.
Exactly. And that single design choice is called positional encoding.
Positional encoding.
Yeah. And how you choose to inject that positional data dictates the maximum context window, the computational cost, and the overall generalization capabilities of the model.
Okay, let's look at this like a developer facing the problem for the very first time.
Okay.
If I need to inject position into a token's vector, I am probably going to pitch the most obvious hard-coded fix.
The naive approach.
Right. Why not just append an array index?
Just add a number.
Yeah. The token at position 0 gets a 0 added to its vector. The token at position 500 gets a 500.
Makes sense on paper.
It's incredibly simple to implement. Why doesn't that fly?
It seems like the logical first step, but it breaks down rapidly when you apply it to high-dimensional neural networks.
Okay. Why?
Primarily for 3 reasons that our sources outline. First is the magnitude problem.
Magnitude.
Yeah. If you add a massive integer, like 500, to a token's embedding, that massive numeric value completely overwhelms the delicate, finely tuned semantic meaning of the token.
Ah, I see. So it's like turning the bass up so high on your speakers that you literally cannot hear the vocals or the melody anymore.
That is a perfect analogy. The meaning of the word gets washed out by the sheer volume of its position.
Okay, that makes sense. What's the second reason?
The second issue is generalization. If you train a model by appending integers, and your training data only ever goes up to 1,000 tokens.
What happens when a user inputs a sequence of 1001?
Exactly. The model has no mathematical framework for a number that large.
It's like an out-of-bounds error in a fixed array.
Yep. It completely fails to generalize. It just panics.
And I imagine just adding raw numbers doesn't really give the attention mechanism a good sense of distance either.
That is the third failure point. Mathematically, positions 50 and 51 are close,
Right.
but so are 50 and 49. In the continuous high-dimensional space these models operate in, simply adding raw integers doesn't give the system an intuitive geometric way to distinguish one step ahead from one step behind.
Because it's just a raw value.
Exactly.
So a naive index addition is out.
It's out.
Which brings us to 2017, the original Transformer paper, and a wildly clever mathematical workaround.
Sinusoidal positional encodings.
Right. They decided to use sine and cosine waves. Now, I read through the clock analogy in our sources, but how does this actually map to a 512-dimensional vector?
The clock analogy is probably the best mental model we have for this.
Okay, walk me through it.
Think about an analog clock. You don't just have a single hand tracking total seconds.
Right. You have a system of hands.
Moving at different frequencies. The second hand moves very fast, completing a cycle every minute. The minute hand moves slower, taking an hour.
And the hour hand is incredibly slow, taking 12 hours to complete one revolution.
Exactly.
Right. And by looking at the combination of those three hands, you can uniquely identify any specific second in a 12-hour period.
Yes.
Like 3.45 in 10 seconds looks completely distinct from 3.45 in 11 seconds.
Precisely. And the sinusoidal encoding scales that exact principle up to hundreds or thousands of dimensions. Thousands of hands on the clock.
Exactly. For every single position in a sequence, the architecture creates a vector made of sine and cosine values oscillating at different frequencies.
Okay.
The first pair of dimensions in this vector oscillates incredibly fast, like that second hand.
Up and down.
Right. The next pair moves a bit slower. And the final pairs of dimensions move so slowly they might take tens of thousands of positions to complete a single cycle.
I want to make sure I'm visualizing this correctly. So the formula divides the position by a denominator, right?
Yes.
Something like 10,000 raised to the power of a fraction based on the dimension.
You've got it. That denominator controls the wavelength.
Okay.
For the early dimensions, the denominator is close to 1, resulting in a rapid oscillation. The wave goes up and down from -1 to 1 very quickly across positions.
And the higher dimensions?
For the higher dimensions, the denominator grows toward 10,000, stretching that wave out so much that it barely curves over the span of a normal paragraph. The end result being that every single position, from 0 to theoretically infinity, gets a totally unique mathematical fingerprint.
A unique fingerprint, exactly.
Nearby positions have similar fingerprints, and distant ones look vastly different.
Right.
But here is what I don't get. If we take this complex sine wave fingerprint and just add it directly to the word's embedding vector,
Yes.
doesn't it muddle the data? Doesn't the positional paint mix with this semantic paint, so to speak?
It is a totally valid concern, and it goes back to the magnitude issue we discussed with the naive integers.
Right, the bass washing out the vocals.
Exactly. But you have to remember the sheer scale of the high-dimensional canvas here.
Because it's huge.
It is. These vectors often have 512 dimensions, or up to 8,000 in modern models.
That's a lot of space.
It's a massive amount of space. In a space that vast, there is plenty of room for both the semantic data and the positional data to coexist without destroying each other.
Because the waves are bounded.
Yes, the values of sines and cosines are strictly bounded between -1 and 1, so they never overpower the semantic weights. The model learns to dedicate certain subspaces to meaning and others to position.
Okay, that makes sense. The sources also talk about a property related to relative distance.
Ah, yes.
Something about linear transformations. How does a sine wave help the model understand that the word dog is exactly 3 steps away from the word bit?
This is the most beautiful mathematical property of the sinusoidal approach.
Really?
Yeah. For any fixed offset, let's say a distance of 3 positions, the encoding at position 50 plus 3 can be expressed as a linear transformation of the encoding at position 50.
Meaning the math required to jump from position 10 to 13 is the exact same math used to jump from position 50 to 53.
Yes. It allows the model to learn relative concepts from absolute encodings.
That is wild.
Think of it like a piece of music.
Okay.
Happy birthday sounds like happy birthday, whether you play it in the key of C or the key of G.
Because the intervals are the same.
The absolute pitches change, but the intervals, the relative pitch differences between the notes, are identical.
And sinusoidal encodings capture those intervals perfectly.
They do, allowing the attention mechanism to recognize patterns based on distance, regardless of where they occur in the text.
It is stunningly elegant.
It really is.
But in the tech world, elegance often gets replaced by brute force.
Unfortunately, yes.
Because if we look at models that came a bit later, like BERT and GPT-2,
Right.
they looked at those beautiful sine waves and essentially threw them in the trash in favor of learned positional embeddings.
They abandoned the handcrafted mathematical waves for what is essentially a dynamic lookup table.
Why would they do that?
The logic was simple. If the model is already learning the best mathematical representation for words during training, why not let it learn the best mathematical representation for positions, too?
So position 0 gets a blank vector. Position 1 gets a blank vector.
Exactly.
And the model tweaks those vectors via backpropagation during training to figure out what works best.
Yep. Let the gradient descent sort it out.
I can see why engineers love that. It's incredibly simple to implement, just an array mapping.
Very simple.
But there's a massive architectural wall you hit with this, right?
A hard wall. A really hard wall.
What happens?
If you train your model with a maximum sequence length of 512 tokens, position 512 is a literal void.
Wow.
The model has absolutely no mathematical representation for it. It's undefined territory.
And this connects directly to the pain points software engineers face every day.
Oh, constantly.
You have a massive React component or a huge JSON file, and you want to drop the whole thing into the prompt to ask the model to refactor it.
Right.
But self-attention is an ON squared operation.
Let's break down that bottleneck.
Yeah, please.
ON squared means that as the sequence length grows, the computational cost doesn't just scale linearly, it squares.
So if you double the number of tokens,
you quadruple the amount of math required because every token has to compute a dot product with every other token.
Which means training a model from scratch on 100,000 tokens is financially prohibitive.
It costs millions.
You are forced to train on smaller context windows to save compute.
Right.
But because of those hard-coded learned embeddings, if you train a model on 2,048 tokens, and suddenly a user pastes in 4,000 tokens of code,
the model just hallucinates.
It forgets variables, it outputs total garbage.
Because it literally does not know what position 2049 is.
It's just falling off the edge of the flat Earth.
Exactly. And this length generalization problem, the inability to handle texts longer than the training data, is what drove the industry into a frenzy to find modern solutions.
It was a crisis of scale.
A total crisis.
Yeah.
And the two most influential approaches to emerge from this were ALiBi and ROPE.
Let's look at ALiBi first. Attention with linear biases.
Okay.
It seems like a completely different philosophical approach to the problem.
It really is. ALiBi basically said, forget positional embeddings entirely.
It's just Scrabble.
Yeah. Don't add sine waves, don't use lookup tables, leave the token representations alone.
Then how does it know position?
Instead, let's modify the attention scores directly after they're calculated by adding a proximity penalty.
A proximity penalty. So if token A is attending to token B, and they're really far apart, their connection gets nerfed.
That is the mechanism. If token I is computing its attention score with token J, ALiBi applies a linear penalty.
It subtracts a value.
Proportional to the absolute distance between them. The formula introduces a slope, a negative value multiplied by how many steps apart they are.
So words that are right next to each other get a very small penalty, so their connections stay strong.
Right.
And words that are 100 tokens apart get a massive penalty, suppressing their attention score.
It's like a decay function for relevance.
I can see the appeal for generalization. Since it's just a linear penalty based on distance, it technically scales infinitely.
It does.
If you input 10,000 tokens, the penalty just keeps growing. It doesn't throw an out-of-bounds error.
It boasted incredible length generalization for that exact reason.
But there's a downside.
There is. A strictly linear penalty assumes that distance is the only factor in whether two words should care about each other.
Oh, that's not always true.
Not at all. In complex code bases or long legal documents, a variable defined on line 10 might be absolutely critical to a function on line 1000.
Right.
A harsh linear penalty might suppress that necessary connection simply because of the physical distance.
Because it's too far away on the page, even if it's logically connected.
Exactly.
Which opens the door for the undisputed heavyweight champion of modern open-source AI.
Ropey.
Rotary position embeddings. Llama, Mistral, Quinn, they all use Ropey.
They do.
And it represents a massive shift. Instead of modifying the embedding before attention or penalizing the score after attention, Ropey encodes position inside the attention computation itself.
Ropey relies on a geometric insight rather than an additive one.
Geometric.
Yeah. It represents position not as an addition to a vector, but as a rotation in the embedding space.
A rotation, like physically churning it.
Imagine taking the query and key vectors and physically rotating them by a specific angle. The further along in the sequence a token is, the larger the rotation angle.
So if we go back to our clock hands, instead of adding the time to the vector, you are physically spinning the dials.
Spinning the dials, yes.
Ropey takes pairs of dimensions in the query and key vectors, treats them like a 2D coordinate plane, and rotates those coordinates by an angle that is strictly tied to their sequence position.
And different pairs of dimensions are rotated at different speeds, utilizing those geometric frequencies again, much like the sinusoidal approach.
Okay.
But here's the magic trick of Ropey.
What is it?
When you compute the dot product between a rotated query at position M and a rotated key at position N, the mathematical result inherently depends only on M minus N.
Wait, really? The absolute positions just cancel out in the math?
They do. By applying the rules of complex arithmetic and 2D rotation matrices, the dot product of the two rotated vectors simplifies beautifully.
That is incredible.
The absolute positions disappear from the result. The attention score is purely a function of the relative distance between the two tokens plus their semantic alignment.
That is brilliant. The attention scores natively have relative position baked right into them, without needing extra parameters.
And it is highly computationally efficient.
But that leads to a major question about what we see in the market today.
Okay.
We constantly see marketing materials touting a 200,000 context window or a 1 million token context window.
Right.
What is actually happening under the hood? Because we know they didn't train that model from scratch on 1 million tokens.
They definitely didn't. It is an illusion created by some very clever engineering.
An illusion.
Yeah. When you push a model past its training context length, we know learned embeddings just crash.
The void.
Right. Sinusoidal encodings mathematically work, but the model hasn't been trained to interpret those massive stretched out wave patterns, so its performance degrades.
But Ropey.
Ropey has a unique property. It degrades gracefully.
Because it's based on relative rotation?
Exactly. A token that is 10 steps behind another token still looks like it's 10 steps behind, even if they are at positions 90,000 and 90,010.
The relative angle between them is preserved.
Yes. The issue is just that the absolute rotation angles at those high positions are unfamiliar to the model, so it gets a bit disoriented.
So how do engineers fix that disorientation? Our sources mention techniques like NTK-aware scaling and yarn.
Yet another Ropey extension.
Right. How do those actually trick the model into reading an entire book?
It comes down to interpolation versus extrapolation.
Okay.
Extrapolation is trying to guess what happens past the edge of the map. That is hard.
Right.
Interpolation is filling in details within the map you already know. NTK-aware scaling and yarn essentially manipulate Ropey's rotation frequencies to mathematically compress the massive new position space into the original training space.
Like shrinking the map so the new territory fits inside the borders the model is already comfortable with.
That is exactly what it is. Think of it like a compression dial. If a model was trained on 4,000 tokens, and you want to give it 8,000, these techniques adjust the rotation speeds so that a token sitting at position 8,000 in your extended prompt gets rotated by the exact same angle that position 4,000 would have gotten during training.
Oh, wow. So to the model, it feels like it's operating within its original 4K limits.
Precisely.
You compress the angles, maybe run a tiny bit of fine-tuning, and suddenly a model trained on a small context can handle 128K or beyond.
That is a massive win for efficiency. It is the primary reason we have seen such explosive growth in context windows over the last couple of years without requiring astronomical leaps in hardware for training.
And before we wrap this up, it is worth pointing out that this fundamental problem, injecting sequence into a set-piece system, is not just about text.
Oh no, the core tension is universal across modalities.
It really is. If you look at vision transformers analyzing medical scans or autonomous driving feeds, they use 2D grid encodings.
Right, because images aren't a single line.
They have to inject X and Y coordinates so the model knows a tire patch is below a window patch.
And audio models rely heavily on temporal encodings to understand the flow of sound waves over time.
Even in biology.
Yes.
Protein models, like AlphaFold, they need to track the exact sequence of amino acid chains because a protein's function is entirely dictated by its 3D folding structure, which is driven by that sequence.
And graph transformers, dealing with complex networks like social media connections or molecular structures.
What do they use?
They use specialized encodings based on random walk distances or node degrees.
It's all the same problem.
The underlying architecture remains position agnostic by design. You have this incredibly powerful, parallelizable attention mechanism, and you are forced to build a bridge to reality.
So for the software engineers listening, this entire topic is a masterclass in system design.
It really is.
The transformer superpower is parallel processing.
Yeah.
But human reality requires sequence.
Positional encoding is the vital bridge between those two realities.
And it serves as a powerful reminder of how a single mathematical preprocessing choice,
whether you append a hard-coded integer, map a sine wave, or implement a geometric rotation,
it dictates the maximum context, the generalization capability, and the sheer computational viability of an entire multi-billion parameter system.
It is just a preprocessing step, but it essentially rules the entire architecture.
Which leaves me with a somewhat provocative thought for you to mull over during your next coding session or architecture review.
Let's hear it.
If self-attention inherently ignores sequence, and we as an industry have to spend so much engineering effort mathematically hacking position back into it through complex rotations, linear biases, and frequency scaling.
Yeah.
Does that mean the ultimate perfect architecture for sequence processing hasn't actually been invented yet?
It is a phenomenal question. It suggests that while the transformer is currently the undisputed king, its foundational limitation means there is still room for a paradigm shift.
There is always more to learn, and the foundation is clearly still being written. Thanks for joining us on this deep dive into the underlying machinery of AI. Keep building, keep questioning, and we will catch you on the next one.